lecture. So let's start some definitions on the electrical circuits. So there are some definitions related to it, and we need to know what does this mean and how we can find it. So those definitions are important in solving the electrical circuits. So one of these definitions is called node. So what does node mean? It is any connection between two or more circuit elements. What are the circuit elements? We already discussed this before, which is it can be resistor, inductor, capacitor, voltage source, current source. So whenever you see any connection between two or more, this is called node. For example, when we have this resistor R1 and another resistor R2, the connection between them, this is called node. This is node. Any connection between two or more. Or when I have R1, R2, R3, these three elements are connected in this point, and this point is called node. Okay? So whenever you see any connection between two or more elements, this is called node. Let's have a look here. How many nodes in this circuit, and let's identify them. So let's look in the left-hand side. This one, we have connection between R1 and I1. So this is a node. Let me make a zoom. Then we have, this is the bottom node. There is the upper and the lower node. So we have, how many nodes now we have? Two. Okay, how about this circuit? Let's identify the nodes. There is R1 and I1 here. And there is R1 and I1 on the other side. So how many nodes do we have? Two, another two. Okay. Now this circuit. Let's try to make the connection. So we have V1 and R1 connected here, right? Then we have I1 and R2 connected here. Do we count this as two different nodes or the same node? The same node. Why? Because there is no elements here. If there is no element, they will be counted as the same node. So this will be the same node because there is no element. So you will keep going. Is there any elements? No. Then stop until reaching an element. Is there any element? No. Then stop here. Then all of this blue color is all sharing the same node. Even though someone can say there is a connection here, connection here, connection here. The answer is between these connections, there is no elements. Because the node, it must be connection between two or more elements. Since there is no connection between these 3 points, then they are all the same node. Or in other words, they'll call it like short circuit. They are all short circuit because there is no element, then they are all connected to each other. Okay? So just keep going to see a node. So they are all sharing the same node. Now, how about the lower corner? So the lower, so let's start from here, the corner. Then there is no elements. Keep going. We stop until reaching an element, then keep going, stop, reach element, then keep going, stop until reaching this element. So overall, how many nodes?
Two.
Two. How about the circuits? Let's start here. This is a node. So you will keep going until reaching an element. So start from this element. Here we reach an element. This is no element. Keep going until reaching an element. Then this is another node. What else? Here. This is a node. Then keep going. This is a node as well. So you'll just keep going until reaching an element. Then here, this node, there is a node. Then the last one is this. Okay, so overall 1, 2, 3, 4, 5. 5 nodes. Okay, does this make sense? Now the last circuit, it's your turn. Try it and tell me how many nodes. Okay, how many nodes? 4. Right. How? Let's explain it here. This is a node. This is a node. This is a node. And the last node. So 1, 2, 3, 4. Okay? It's very important to determine how to determine the nodes, not only the number of the nodes, to determine the nodes, because we will use this later in solving the electrical circuits. Okay, perfect. Let's go to another definition. So we have loops and meshes. What do you mean by loops? What do you mean by meshes? Loops related to any closed path. Through a circuit, when you go to any closed path, such that we will not cross more than one. So just make sure to complete, don't go spiral, just complete the circuits. Complete the circuit closed path. While meshes is a special case of loop, which is a mesh is a loop, but it should be only inner loop, not outer loop. What do I mean by this? Let me give you an example. Assume we have this voltage source, this resistor, another resistor, then something like that. Now, we need to determine the number of loops, or determine the loops. So we have this loop, right? And we have this loop. So far we have 2 loops. Is there any other possibilities for a closed path other than these 2? Yes, there is what? The outer. So the overall number of loops equals to 3. Now, how about meshes? Number of meshes, it is related to the number of inner loops. So look at the outer loop, which is the purple loop. Does it include any loops inside this? Yes, there is the green loop and the red loop, right? Since there is 2 loops inside it, therefore it's not considered as mesh. It's considered only as loops. So as a result, how many loops do we have? Or how many meshes do we have? We have only green and red. So we have only 2 meshes. Meshes related to number of inner loops, while if there is any outer loop, this is not considered as mesh. Or in other words, there's another definition for the number of meshes, which is number of window panes. So look at this circuit. If we want to make it as windows, how many windows do we have? 2. That's it. Number of meshes, 2. This is another way. Okay? So now, so far, we know nodes, we know loops, meshes. Okay, any question about these 3? Okay, let's go to branch. What do you mean by branch? Basically, branch, which is the connection of an element. So basically, I would say number of branches equals to the number of elements. That's simple. So how many branches, how many elements? However, there is something called essential branch. So essential branch means if there is 2 or more, or actually, yeah, if there's two or more elements sharing the same currents, they will be counted as one essential branch. As one essential branch, shortcut EB. Okay, let's see an example so we can understand this in better. So let's go, or let me write the same circuit that we did in the previous slide. Let me call this is VS, R1, R2, R3, and R4. Okay, so with this circuit, how many elements do we have? How many elements? Yeah, 1, 2, 3, 4, 5. So we have 5 branches. Now, how many essential branches? Basically, you will go back, make another revision, then see if there is any 2 or more elements are sharing the same currents. So I will say there is a current here between VS and R1. So this is one essential branch. Then R2, it's only sharing its own current. There is no current the same, right? So this is another one essential branch. Then we have R3 and R4. They are sharing the same currents. Then this is another essential branch. So overall we have 3 essential branches. Again, how we know that these elements are essential branches or not? Basically, look at the circuits. Whenever you see 2 or more elements are sharing the same currents, then this will be counted as one essential branch. How can I know these elements are sharing the same currents? You can imagine there is a water flow going from here, keep going. The water will not split, right? This means they are sharing the same currents. While at this point, the water will split here and split here. Therefore, these elements will share different currents. Then, with R2 and R3, R3 and R4, if there is a water flowing from R3 toward R4, it will not split, therefore they are sharing the same currents. Okay? Yes?
So which one's the essential branch with R2?
With R2, is there any other element sharing the same currents? No. Then R2 is considered as essential branch. So, in other words, how many different currents we can have in these circuits? 3, right? Then 3 essential branches. This is another way. So again, essential branch is related to the number of the elements that are not sharing the same currents, or the number of different currents in the circuits. Let me give you another example, and I want you to determine how many branches and essential branches here. With this example, this circuit, how many essential branches do we have? Or how many branches? Let's start how many branches. We have R1, R2, R3, and voltage source. So we have 4 branches. How about essential branches? 1. Why? They are all sharing the same currents. So they will be counted as one essential branch. Okay? Okay, this is a cumulative example here. How many loops, meshes, branches? I would like to add to essential branches. nodes as well. So it can be cumulative. Let's look at the circuit. Let's determine the nodes. How many nodes do we have? There's upper node, lower node, then we have lefts and rights. So we have 4 nodes, right?
3, 2, yeah.
Okay. How many loops do we have? 3. How? There is this loop, loop 1, this loop, loop 2, and we have the outer loop, which is loop 3. Therefore, we have 3 loops. How many meshes?
2 loops.
Because we have 2 window pans, so 2 or 2 inner loops. How many branches?
5.
1, 2, 3, 4, 5. Yes, 5. So keep in mind, you need to count everything. The sources and the resistors. So voltage source, current source, resistors. So we have 1, 2, 3, 4, 5. 5 branches. How many essential branches do we have? 3. How we can judge? So this is its own currents. These 2 are sharing the same currents. These 2 are sharing the same currents. Therefore, we have 3 essential branches. So what else? We just found loops, meshes, branches, essential branch nodes. Yes, that's it. That's cumulative example. Okay? In Wednesday quiz, there will be part of the question, or the first half of the question, which is determine number of loops, meshes, essential branch, something like that. So you will see it in the quiz, and I think you will see it in the test as well, in the first exam. Yes?
Will the number of loops always match the number of essential branches? Or
It's not necessary. Okay, any question about branch, loops, essential branches? Now let's go in more fun things, which is Kirchoff's laws. So Kirchoff's laws, you are familiar of this from physics. And I think in physics you apply this in you apply this in some pattern or some procedure. Right now in electrical engineering, we will use our own procedure. We will not use what you have learned in the physics. This does not mean in the physics is wrong, no, it's correct. But in the physics, they are doing this in different way, while in electrical engineering, we are trying to standardize how to treat or how to solve the circuit analysis. So we will solve this using our own approach. So, I mean, in solving the circuit, sometimes we can go clockwise, counterclockwise, or voltages different, or something like that. But we need to make or regulate these things. So I can solve this circuit in the same way that you are solving this, in the same way the other things that the other student or other people that can solve it. So we are trying to make a standards so we can solve this in more organized way. And in my point of view, I like the way that we are doing this in electrical engineering, because we are doing this in standardized or in some procedures that are clear and easy to understand, and I think it will be easier than physics. Okay, let's start first with the definitions that I know that you are already familiar with this, but let's go in deep detail. So Kirchoff's laws. So we have Kirchoff's current law. As a shortcut, we will call it KCL. So we'll no longer say Kirchoff's current law, we will say KCL. And Kirchoff's voltage law, KVL. Starting from now, I'm going to call them KCL and KVL. KCL related to conservation of charge. That's why it's related to the currents, because the current is the charge, how is the charge moving, or the charge rate, okay, or the electrons moving. Then we have KVL, which is the conservation of energy, because voltage is related to like the energy transfer capability, or the time derivative of the work, or time derivative of the energy, or the energy rates. So as a result, I will say that it is the conservation of energy related to KVL, conservation of charge related to KCL. So electricity is conservative, then we need to apply KCL and KVL. We cannot produce energy from nothing or generate energy from nothing. The energy will be transferred from one shape to another shape. For example, to generate the electricity, we will convert the fossil fuel into when using the combined cycle or to steam turbine, etc. Then this is kind of maybe will goes make the turbine rotating. Then we have mechanical energy. Then the turbine is connected to the generator, which is making this, converting mechanical into electrical energy. Then the electrical energy will go through the wires. Then we will consume this, for example, as lights. So the light bulb, for example, will consume the energy, will go as light, as we see, and it will go as heat. So the heat will go, it will not be significant, but it will go to our environment and so on. So the energy will be transferred from one form to the another. Even though that we heard a lot about losses, so there are a lot of losses going on, most likely these losses go sometimes as heats. So the losses that goes in the wires as heat. The other thing goes as heat. So the energy again is conservative and transferred from one shape to another. Let's go to KCL. KCL basically, we used to say the algebraic sum of the electrical currents entering the nodes, and we know what does node mean, any connection between two or more elements, entering any nodes is equal to the algebraic sum of the currents leaving the nodes. So the current in equals the current out. Or if we assume the sum of the input currents will be 0, or we can assume the sum of the output currents will be 0. So we have three ways. Okay, so how about when I say the sum of output current will be 0? How about the input currents? The input currents, we will put a negative sign. Because if you see any currents opposite of your assumption, then you will put a negative sign. So we have three different ways. In order to regulate our analysis or to make sure that we are all on the same page, we will use this approach. Use this. The sum of the leaving currents will be 0. That's it. That's what we will use. So we will make it as a standardized. So let's assume this. So we have here is IA, IB, IC. And I'm going to observe this node. I'm going to call it node 1. So I'm going to apply KCL at node 1. Keep in mind, KCL will be applied only at a node. So again, this is sometimes something can be new for you, but that's how we will apply it here. We will apply KCL at a node. According to the KCL in our standards, the sum of the leaving currents equals to 0. So we are applying at node A. Our observation is node A. Look at IA. Does IA entering or leaving the node 1? It's entering. The law says its leaving currents will be 0. So what should I do? It's entering, but it's the sum of the leaving will be 0. What should I do? It is the opposite of my definition, right? The law says the sum of leaving will be 0. I find a current entering, then I will do the opposite. What does the opposite mean in vectors? Negative sign, right? Since IA, it is entering, not leaving, while my law says it's leaving, then I will put negative A. Now, how about IB? Is it entering or leaving? Leaving. So it's the same as my assumption, so plus IB. How about IC? Leaving, right? Leaving node 1. So plus IC equals to 0. That's it. The sum of leaving currents will be 0. Whenever you see any current entering, you will put a negative sign. That's it. Another representation, which is when we have, for example, here, the same 3, but I'm going to assume IA like this, IC like this, IB like this, and here is a node 1. Now we need to apply KCL at node 1. the sum of the leaving currents equals to 0. Now look at IA. Is it entering or leaving? Leaving. So IA is positive. How about IB? Leaving. So plus IB. How about IC? Leaving. Plus IC equals to 0. Then that's it. Somebody can say, okay, look at IA, IB, IC. All of them are leaving. This does not make sense, right? I mean, according to charge law, there should be something entering, something leaving. So, is this correct or not? In our equations, it can be correct. In applying KCL, it can be correct. So, what's the point? Let me tell you this scenario. Let's assume IC equal to 1 ampere, IB equal to 2 amperes. Now I need to calculate IA. According to the KCL, IA is still unknown. IB is 2 amperes, IC is 1 ampere equal to 0. Let's calculate IA. IA will be negative 3 amperes. And the negative mean opposite direction. So whenever you see this in the circuits, like all of these currents are leaving the nodes or entering the nodes, and there is no other currents, don't worry about it. I mean, according to KCL, it still can be correct, but definitely one of them must be negative. And the negative means the opposite direction. So, you will see one of these values. Whenever you see any current has a negative value, means the real life is the opposite. So IA is negative 3. Therefore, the real life direction is the opposite way. Then now it makes sense. Right? So again, when you apply KCL or KVL, don't worry about these problems like all of the currents are entering, all of the currents are leaving. That's fine. If your answer is correct, you will get a negative sign in one of them. And one negative sign means, as we see here in IA, the negative sign means opposite direction. Okay? Any question? Yes.
Does it matter which one you pick? Like which one of those coming in you pick, IA, IB, or IC, that's going to be negative, or is it going to be any of them?
So here, in this example, I assume IA equal IC equal 1 ampere, IB equal 2 amperes. So definitely it will be one of them. You cannot pick. I mean, here I just give an example. But during the circuits, there will be one of them. Which one? We don't know. During our analysis, you will realize. Now another example for KCL, which is, here it is, 4 points. This is node A, the node 1. Then we have I1, I2, I3, I4. Now we need to apply KCL. At node 1. This is node 1. So what do you think KCL will be? Sum of leaving currents equals to 0. Then I1, is it entering or leaving? Entering. So we'll put negative sign, right? How about I2? Negative I2. I3? Negative I3. I4?
Entering.
So minus I4 equals to 0. That's fine. So during our analysis, all of these currents are entering, but in real life, you will see one of them negative sign, or maybe 2, maybe 3, we don't know. But there should be something that makes sense later once you do the analysis. Okay, so that's KCL application. Let's go to KVL. Okay. KVL, algebraic sum of the voltages rises around any loop is equal to algebraic sum voltage drops. So there is voltage rises, voltage drops, or the sum of the rises equal to 0, or the sum of the drops equal to 0. In order to avoid the confusion, is it rises or is it drops or something like that, we will use only this. We will use this. Okay. And when you travel on the loop, also, KVL will be applied only at a loop. At a loop, not at a mesh, at a loop. So it can be any closed path. You need to have a closed path. No matter if it is inner or outer, you still can apply KVL. That can be fine. So we will use the sum of voltage drops will be 0. So when we apply in at a loop, we need to travel either clockwise or counterclockwise. So in order, again, to standardize our analysis, we will use only clockwise. We will use this as well. We will travel clockwise. And also, to standardize this, we will start from the left bottom corner. Clockwise, and start your KVL from the left bottom corner. So we will make our KVL to standardize this, make it around the loop, travel clockwise, start from the left bottom corner. Now we will assume all of the voltages are given, all of the voltage directions are given, all of the current directions are given. Later, we will learn how, maybe, I'm not sure if it's this lecture or next lecture, we will learn how to make the current directions or voltage polarities. So, look at this example. This is one loop. We need to apply KVL at this loop. So in order to apply KVL, it must be around a loop. So here is a loop, KVL. Around this loop, we will travel clockwise and start from the left bottom corner, which is here. Okay? And go clockwise. And we used to write Greek numbers like loop 1, loop 2, like 1, 2, 3, whatever, like 4, something like that for the loops, to determine the number of the loops. So in loop 1, we will start from the left bottom corner, then we will apply KVL. So we will write like this. Whenever we apply KVL, you need to write this statement. KVL at loop 1. So the sum of the voltages goes to 0. We will travel clockwise. So let's start clockwise from here. Start from this point and go back to it. So I'm going to travel clockwise. I'm starting here. I hit the negative sign, right? So the negative sign of the voltage. So I will write negative V1. Okay? Now I'm done with V1. Keep going. Start here. I hit the positive of V2, right? Therefore, I will write plus V2. Now I'm done with V2. Keep going. I hit the negative sign of V3. Is this correct? So I will put minus V3. Then keep going. No more elements. I'm back to the origin. Okay? So since I'm back to the origin, no more elements, then equals to 0. Okay, so the procedure is simple. You need to be consistent. Go clockwise. Start from the left bottom corner. Whenever you see any other KVL, also you need to be consistent, such that start from the left bottom corner, then travel clockwise. When you hit the negative sign, put a negative. When you hit a positive sign, put a positive. Okay? Any question about KVL? Okay, there is an example here to do KVL and KCL. Solve for I, V20, VD. You need to locate where is I. Here is I. Where is V20? Here is V20. Where is VD? Here is VB. So you need to look at where all of these. Now, you need to apply KVL or KCL such that there is only one unknown. Okay. Let's first try to find the currents. So again, the procedure. Apply KVL or KCL such that there is only one unknown. Otherwise, we cannot do it. Let's do KCL at node 1. Do you think is it a good idea to apply KCL at node 1? There is a current here, they are all sharing the same current. So it does not make sense. There's no point. I mean, what's the point of doing this? So there is no point. How about applying KCL at node 2? Do you think is it a good idea? Let's see. Do we have only one unknown or not? This current is unknown. This current is known. This current is known. Then perfect. That's what I want. Look for a KVL or KCL such that there is only one unknown. Then when you do KCL at node 2, this is a great approach. So I will say I'm going to apply KCL even when you do this in your analysis, like in your homework, in your quizzes, exams, you need to write this statement that I'm going to apply KCL at node 2. You need to write this. So the grader or the instructor or even yourself, when you go back and read your answer, you can understand where are you applying your KVL or KCL. So KCL at node 2, the sum of leaving currents equals to 0. Now look, start with I. Is I entering or leaving? Entering. So it is negative I. How about the 7 amperes? Is it entering or leaving? Leaving. So plus 7. How about the negative 3? Is it entering or leaving? It's leaving. So we will put plus, then keep in mind we'll put negative 3. Okay? So entering and leaving is something different than the sign itself or the value itself. So it's positive because it's leaving. But the value is negative 3, so we'll put negative 3. Okay? So plus negative 3. Then there is no other currents equal to 0. Again, it's plus negative 3, positive or plus because it's leaving, and negative 3 because the value is negative 3. So I will be, we will move it to the other side, 7 minus 3, which is 4 amperes. Now we are done with the first unknown, which is calculating I. The second unknown, which is, we need to know V20. V20 is the same as the voltage at element C. How can I know V20? Or VC? The voltage is KVL, yes.
KVL of the loop 1 left.
Yeah, so let's make the loops like, this is loop 1, this is loop 2. And we have the outer loop as loop 3. Okay, so, yes, correct. You said like loop 1. Why? Because when we do KVL, VA is known. We know it's negative 30. VB is known, which is 70. V20 or VC is unknown. Then that's good approach, which is there's only one unknown. How about if someone say, can I apply KVL at loop 2? Do you think it's correct? Loop 2? No, we have 2 unknowns. We have more than one unknown, so we cannot do it. Therefore, let's do KVL at loop 1. Loop 1. Again, make sure to write the statements, KVL at loop 1. And according to our procedure, start from the left bottom corner, then go clockwise. So start from this corner, then we hit a negative sign, so we will write it as negative VA. Then keep going, positive sign, then plus VB, then keep going, positive sign. So it will be plus VC. Then I'm done. This is the end, right? So it will be equals to 0. So I'm gonna erase this because I don't want to make a big mess. Okay. So negative VA plus VB plus VC equal to 0, that's our KVL. Because we start from the left bottom corner, then we traveled clockwise. Now, let's substitute the values. VA is negative 3. So it's minus of negative 3. Okay? The sign itself because of the magnitude, or because of the value, and the sign because of the polarity. So two signs are matters. Okay? So negative or negative 3 plus VB, VB equal to 70, VC, which is the same as V20, equals to 0. Therefore, move them to the other side, V20 will be 100 volts. Okay? Second unknown, done. How about the third unknown?
Negative 100. Negative 100.
Negative 100?
Volts.
Okay, negative 100 volts. Let's see. Or how did you find this, actually?
You just move the 70 and the 30 over to the right side.
Yeah, which is making KVL. Okay, let's do KVL at loop 2. Okay? Okay, I'm sorry. Now I get your point. I thought you were talking about VD. I'm sorry.
No, you're good.
It should be negative 100. Yes, correct. Apologize. I was talking about something different. Now, let's find. We are all agree now it's negative 100 volts. Now let's find VD. How can I find VD?
Positive 100. KVL.
KVL loop 2. So KVL loop 2, start from the left bottom corner, then go clockwise. So here there's negative, then we will go, this will be positive. So it will be negative C plus VD. Negative VC plus VD equals to 0. This yields VD equals to VC, which is the same as V20, which is the same as negative 100 volts. Therefore, VD equal to negative 100 volts. That's one approach. There is another approach. If you don't want to apply KVL at loop 2, or if someone gets, say, I'm going to apply KVL at the outer loop, it can be correct. And it will give the same answer. You can apply KVL at the outer loop, and that's right. And there is another approach. I mean, sometimes in the circuit analysis, you can have multiple answers, and they are all correct. I mean, multiple ways, but it will give the same answer. So another way, again, apply KVL at the outer loop, or apply KVL at loop 3, then you will get the same answer. There is a third answer. Can anybody get it?
Negative 100 volts.
Yes. How can I say, can I reach, or I mean, third way to get VD?
Minus VA plus VB and then plus VD.
Yes, this is KVL at loop 3, which is we did here. But I mean, is there any other, or actually there is a third way, but can you figure it out? Anybody can figure it out? Yes?
You can do the big loop with A, B, and D.
Yeah, but it's still the same. I mean, according to our standards, we will do it as KVL, what's called it? KVL, start from left bottom corner, then go clockwise. So there is another way. Yes, can you?
Are you referring to
VC and VD.
because they're parallel?
Yes, parallel. That's what I'm looking for. VC and VD are actually in parallel. And parallel means sharing the same voltage. Therefore, there is no need to say KVL at loop 2 or loop 3. You will say VD equal to VC because they are in parallel. That's it. So again, all of these three ways are fine, and all of them are correct. So VC equals to VD because in parallel. So again, sometimes in the circuit analysis, there are multiple ways to find the answer. This way can take a few seconds, this way can take 1-2 minutes, this way can take 10 minutes. That's the trick in the circuit analysis. And that's the trick maybe in the first exam material, which is you need to figure out how to find it in shorter time, less efforts. Okay? So I'm trying to standardize our answers so we can make sure that the way that you need to think and how to solve a certain problem. So that's what I need you to learn these skills, which is what should I do in order to solve all of these problems. Okay, now before discussing this example, I need to write some procedures in how to write or how to make some definitions or how to start solving the circuit. Like this example in KCL, KVL, not all of the current directions are given, right? We need to find IA. The current directions are not given. The voltages are not given, right? So what should I do? How can I assume them? That's what I'm going to write now, which is how to assume a current directions or voltage polarities. So my topic here is how to assign a voltage polarity and current direction. Okay, this is based on Ohm's law. Recall Ohm's law. We know it's V equal I times R, but whenever we have the currents entering the positive, it will be positive Ohm's law. Whenever we have the currents is negative, it will be negative. So our targets is to make Ohm's law always positive, if possible. If I have a choice to choose a current direction and voltage polarities, I'm gonna make sure everything is positive, so I will not worry about the negative sign in Ohm's law. Okay, how? We need to make sure the currents enters the positive polarity of the voltage. Of the voltage of the resistor. This is for the resistor. How about for the source? The currents should leave the source, should leave the positive, should leave the source. Or in other words, leave the positive polarity of the source. So you will see the source and the resistor are the opposites of each other. They are the opposite of each other. Let me give you a small demonstration. Plus minus Vs. Here is R1. Here is R2. Here is R3. Now I need to assume a current directions and voltage polarities. According to our standards, let's start from the source toward the load. Normally, most likely, the current will go out from the source, will go out from the pressure source, will go out like, assume there is a water pump, the current will go out from the water pump toward the load, right? Or toward the turbine. So the current will be out here. That's why I'm going to call it as IS. Then IS is keep flowing. This remains IS. Then at this point, it will split, right? So it will split here, which is I'm going to call it I2, and will split here, I will call it I3. Then at this point, I2 and I3 will merge together, which will be the same as IS. Okay? Basically, that's how I assume the currents. Okay, does this make sense? It's just easy to follow. Out from the source, then it will split. How about the voltage polarities? I need to make sure all of the currents enters the positive polarity of the voltage. So here, I'm going to change the color. Plus minus V1. Why I make a plus minus V1? So I want to make sure Ohm's law is positive. Then here, plus minus V2. So the current enters the positive. Then here, plus minus V3. So the current enters the positive. That's it. Now all of the current directions and voltage polarities are given. That's how we find them. So now we are done for today. So see you next lecture.